This is the second lecture on the harmonic oscillator for Chapter 2, Ordinary Differential Equations. And in this lecture I will show you how to rewrite those constants, the C1 and C2, for the solutions in terms of the initial values from the initial value problem. So in the previous lecture all we looked at was the differential equation here. Right, we solved it, we were able to reduce it to a quadratic equation, and then we solved it and ended up with these different cases: the overdamped, critically damped, underdamped, or purely oscillatory, depending on the solutions for the quadratic equation, for the characteristic polynomial for this differential equation. And when we wrote the solutions for all these cases, they ended up having constants in them, C1 and C2. For example, for the overdamped case, there were two distinct roots for the characteristic polynomial. We had a lambda 1 and a lambda 2, and the solutions were y of t equals c1 e to the lambda 1t plus c2 e to the lambda 2t. Now we're going to consider the whole initial value problem, which is the differential equation plus these initial conditions. So remember, we have a second order equation. We need two initial conditions, and the two initial conditions will be the value of the function at, I put 0, but it could be any time 0, any particular time that's your start time. So we have the value of the function and then the value of the first derivative. So we want to rewrite these constants in terms of these initial values. After that, all we have to do is evaluate not only any problem that we've written in this form, or we can also evaluate any initial value problem. So for the first case, this is your overdamped case. You can see the typical equation. I wrote it on the previous slide. Here were the solutions, and here's the C1 and the C2. Now, what are the initial conditions that we have? We've got the value of the function at time 0, which we call y0, and then we have the first derivative of the function evaluated at time 0, and we call that y0 prime. Okay, so to evaluate these conditions, we'll need the value of the function, and we'll need the first derivative. So taking this first derivative, we end up with alpha 1 c1 e to the alpha 1 t plus alpha 2 c2 e to the alpha 2t. Okay, before we wrote the roots as lambdas, I'm using alpha. That's all, just change the notation. Okay, it's no problem. And actually I'm doing this because I want to carry it through in the solution so that you'll see the alpha and then you see the omegas when you get to the complex roots. Okay, so now we just take these equations and we evaluate them at 0. I'm writing these steps because I've seen some very good students go kind of balk at this step, at how to evaluate these constants. So as soon as you see it, you'll see it's quite obvious. Okay, so I evaluate these two equations, the value of the solution, the value of the first derivative at 0. I know from the initial condition they have these, what we call values, but right now of course there's no numbers for them. Alright, so I've got y0 and y0 prime of c1 plus c2, alpha c1 plus alpha c2. Now I have to use algebra and a bunch of steps, which I'm not going to do here. It's just boring. At any rate, you can see obviously exactly what to do. You can write c1 equals y0 minus c2, substitute that into this equation, solve for c2. Anyway, here's what you get. c1 equals a negative of, in the numerator you have that first derivative prime, that initial condition, minus alpha 2 times the value of the function at the initial time is divided by the difference of the roots. If you want to think in the old terms, that would be lambda 2 minus lambda 1 if you want to use that notation. And here's the value for c2, which looks fairly similar. No negative sign in the alpha 1 in the numerators. Alpha 2 in the numerators replaced with alpha 1. Okay, so when you write the differential equation, let me clear this board, you can just write those in, which is sort of messy, but y of t equals negative y naught minus alpha 2 y naught over the difference alpha 2 minus alpha 1 e to the alpha 1t. And now you see there's no more c's in there, and when you have a different initial value problem, you just change the values of y0 and y0 prime. This was a prime. Okay, so this is the goal. You don't have constant sitting around. You have to figure out how to evaluate. You know how you want to evaluate them. You want to evaluate them in terms of the initial conditions. And those initial conditions are the value of the function at time 0 and the first derivative at time 0. And if you want to start at a different time other than 0, you can still do that. You can go y at t0 equals y naught. Okay, and then you would just rescale this as t minus t naught for the in the numerator, in the exponent of e. So you can handle a different start time than 0, but it's just as easy to write it in terms of 0. Okay, so that's for the overdamped case. Now this is a critically damped case, and here it's good to just look at these again and recall what these equations are. Alright, for the critically damped case, you had one root for the characteristic polynomial. I'm calling that just plain old alpha before I called it lambda. Alright, and since it's a damping, that's why I like to use alpha. Okay, you had one, I shouldn't say you, we had one solution, and that solution that fell out from the quadratic formula was e to the alpha t, and we needed two solutions, so we used the Wronskian and Abel's theorem to find that y2 was t e to the same root, t to the e to the alpha t. And now, because these are linearly independent, we can write all of the solutions as linear combinations of them, and that's what we have right here. Now we have the same initial conditions. Y at 0 equals y naught. The derivative at time 0 is y naught prime. We want to rewrite the same C1 and C2 in terms of those. So here's the first derivative of, in this case, is alpha C1 e to the alpha t plus C2 e to the alpha t, because you had to take that, use a product rule, plus alpha C2 t e to the alpha t. Now if we solve that at time 0, okay, I'm evaluating this one at 0. Y at 0 is just going to be C1, and I know that's y naught, so we're done. Not much algebra there. We like that. Okay, for the second one, we're evaluating this at time 0. We get an alpha C1. Okay, I know what that is. And then the next term is just going to be plus C2, because this one is going to go to 0 at t equals 0. Okay, and we can substitute from the, we know this is y naught prime from the initial condition, so we can solve for C2, and we get this condition for C2. So, like I say, not much algebra there. It makes it easy. So if you want to write the solution, y0 e to the alpha t plus y0 minus y0 prime, minus alpha y naught t e to the alpha t, and again the c's are gone, and we just have the initial conditions embedded right in the solution. And the next one, of course, is similar. This is for the underdamped case. If you recall, the solutions from the quadratic formula were complex conjugates. Oops. And I was writing them as alpha plus or minus I omega. Then we put them back into and went through the solution, the steps as we did before we ended up with complex solutions. And we didn't want complex solutions, we wanted real ones. So by a judicious selection of these constants, we ended up with two linearly independent real solutions of the differential equation, which were taken as the basis. And those were, oh, that's right, this is e to the alpha t because it's damped. All right, and v of t will be the same, e to the alpha t sine omega t. And now we make linear combinations of those for all of the solutions of the differential equation, because since they are linearly independent, there's a set of two of them for this two-dimensional solution space, they form a basis. Now we have to take the derivative, and again we have to use a product rule here, and then we have to remember to use the chain rule and pull those omegas out. Okay, when you take the derivative, the constants in this case are pretty easy to find because sine of t will go to 0 at t equals 0. That helps. And so c1 equals y naught as before, and here's c2, y naught prime minus alpha y naught over omega, looking very close to what we had for the critically damped case. In the lecture notes, the written lecture notes, I put in a chart showing all these cases and all the conditions on them for reference. I didn't write the C1 and C2 up into the equations right here because it makes the equations kind of unwieldy, and but I wrote them right beneath it, which is okay. I want to point something out here. Look at the case of the undamped or purely oscillatory harmonic oscillator. For the purely oscillatory harmonic oscillator, there is no damping, and the solutions are just combinations of sines and cosines. The 0 on this is omega naught, is used to contrast it with the frequency here when there is damping. Okay, and if you notice what it is, this omega naught is the square root of Q. Okay, this is called the resonant frequency. Obviously you're never going to hit it because there's always damping in the world, but this is the resonant frequency for the harmonic oscillator, and all it is the square root of the Q. Let's write that equation again so you can remember that. Here was that differential equation in standard form, so you can identify what is P y by dt plus Q. So it's and we're working with a homogeneous case here. So it is the coefficient of the y term in the differential equation. The square root of that is the resonant frequency. Okay, in the next lecture I'll apply these results to an RLC series circuit.